Hey everybody, welcome to PCB routing on Saturday, on Sunday. I have kids and they're very unpredictable, and so I wasn't able to make it yesterday, but we'll make it up for it today. Let's see. Um, Hold on, looks like I have a problem streaming to YouTube. I'm sorry, I'm relatively new to this. Okay, well, I think I'm just going to have to upload it to YouTube after the fact because I don't think I have time to fix this live. So let's get right into it. Last time we got pretty far with our PCB. For those just tuning in, we're making an industrial Ethernet switch. We have power and input filter stuff over here, and EMC compliance stuff, and so on and so forth. In the last two episodes, we went into that in some depth, so check there if that's interesting to you. And then we have here we have our network chip. It's an 8-port Ethernet chip, and then here we have one power of Ethernet controller. And here we have another power of Ethernet controller. How power of Ethernet controllers work, we looked at last week as well. So basically what we have left to do on this board is a whole bunch of routing. We have to connect the Ethernet chip to all the Ethernet magnetics. We also have to route the power over Ethernet stuff. And I think we'll start with the power over Ethernet stuff going around the very outside. And so here we have Ethernet magnetics. And the power of Ethernet is going to be coming in on the center taps, or sorry, going out on the center taps of the connector side of the Ethernet magnetics. And so here are the center taps, pin 15 and pin 10. So the first thing we want to do on those is make sure that we're not susceptible to any overvoltage coming in over that line. Is this big enough? Let's make one big fat track and connect it to this TVS diode. As we talked about in the last couple of episodes, TVS diodes, or transient voltage suppression diodes, are there to basically turn any voltage over a certain threshold into heat so that they don't mess with any of the electronics inside the board. So if lightning strikes or somebody touches the connector and then has electrostatic discharge or something, then the diode will turn that into heat rather than turning it into magic smoke in other components. Right? The default for TVS diodes is also to fail closed. So if the diode does break, then it will short circuit. It'll melt. The internals are set up so that if it gets too hot and melts, that the input and output will melt together, and so they're connected. And so, yeah, if you have electronics that doesn't work anymore and basically blows a fuse immediately whenever you turn it on, try removing all the TVS diodes. It might just work again. Okay, so here we have, for turning it on, we have a fuse. If we look in the schematic, oh yeah, we crashed last time. It looks like everything for the Vive though. I was using the 9.0 version of KiCad last time, so I was kind of asking for it. But now we've got it all upgraded, so it shouldn't crash again. So here we have the circuit for the power over Ethernet. Right? We have power over Ethernet plus is fixed, right? And we're switching the low side. since the other side of the wire is required by the standard to be isolated anyway. It doesn't really matter if we switch plus or minus, the plus or the minus side. And since it's easier to switch the minus side, because NPN transistors are a little bit cheaper and easier, and because then we don't have to worry about switching at a voltage much higher than our own ground, right? So we're switching the minus side. And so we have our filter capacitor and TVS diode here, saving us from electromagnetic interference. And then we go through our fuse to make sure that if somebody shorts the output, it won't damage any of our electronics to the point where something burns or something, right? I mean, technically everything's a fuse, right? Transistor's also a fuse, but fuses fail in a lot more happy states than other components might fail, right? So 500 milliamps at 48 volts is plenty fuse if we are nominally 15 watt output, right? The controller chip will actually also has a power monitoring thing and should shut it off if it gets over 15 watts. You can actually set thresholds via I2C on this controller chip. So whenever it's over some preset threshold, then it will turn it off anyway. So the fuse is just to make sure nothing goes wrong, right? I mean, in an ideal world, they would never blow. The chip would turn it off first. So we have here our fuse and here our TVS. And so here we have our filter capacitor, just to make sure that any high frequency noise and whatnot. And so I guess the question is how we incorporate this best. I guess we could put it like there. I mean, the considerations to take here is that we don't want to put it towards the outside world from the transient voltage suppression diode, right? Because otherwise, voltage drops in the wires to the TVS diode could fry the capacitor, right? It's probably something like this. This is a little suboptimal because as we got into last time or the time before, it's not intuitive actually how far vias are, right? Like for a frame of reference, this track is 1 millimeter wide and the board is 1.6 millimeters thick, right? So this track is about as far in the Z direction going to the back of the board and then coming back to the front as it is in across, right? So that's a little non-intuitive when you're routing boards, just how far it is to get to the other side of the board. But on the other hand, the outside world is through magnetics from us in this case, and so just for getting your gut feeling all calibrated. It's once there's some inductive resistance between you and the outside world, then you're not going to be getting as much or having as many problems as you might otherwise have. So this is fine, right? So okay, so we want probably a big thick track. Distributing power, can we scooch underneath? Yes, we can scooch underneath, so we'll just keep doing that going around, scooching underneath, and might just be my OCD or whatever, but it's nice to build everything up symmetrically, right? So there's the fuse. Let's connect all these up, make it a little bit pretty. That's actually not so pretty. I mean, this is obviously doesn't matter, and it's just to be beautiful, but somehow my brain doesn't let me make it ugly. Okay, if you want to still stay symmetrical, I guess it doesn't really matter that we're such fat tracks. We got the space here. Okay, so there's the next one. Where's its fuse? Is that it? Yeah, that's its fuse. So just keep going around the horn. There's a lot of redundant routing here, so I hope you like just watching me without giving advice on everything. It's the same circuit again and again and again. And I hope you all had a nice Saturday. Life with kids sometimes gets in the way of schedules, but I'm very happy to have them. I would suggest kids to anyone. Obviously, this is not PCB advice, but not having kids in life is like playing some RPG and then just, I don't know, staying in one part and never actually finishing the game. They teach you a lot about yourself. Okay, let's see, what do I do in this case? So that's the one that's kind of sitting there in the middle of nowhere. Oh, well, I guess these things are not that tall. They can fit under the plug. If you don't know what I'm referencing, then look at the older videos. There's these plugs that are up on stilts, and they got some pins between the board and the plug. These guys. So we do have room underneath. We just don't have room for these magnetics because they're pretty tall. So where are the other pieces? Oh yeah, there they are. So what we're going to do, fuse over here like, okay, so that's going to be going to that one, so it's going to be going left. So why don't we just put that on here on the left side. Capacitor. I'm going to try and get through relatively quickly this time because we want to get to the full beginning to end design next week, or probably over the next 3 weeks. We should be able to get it in 3 weeks, which, considering we're 2 hours every one of these, then 3 weeks is 6 hours. That's it's not bad for a new product, right? But yeah, there are certainly some tricks that we'll see along the way, which make us a lot faster when it comes to designing things. Okay, yeah, we're now in the middle again, but we can't quite use the same trick because let's see. So those are going that way, and so I need to get around that with these tracks here, going like that to the connector, but that should be okay. So I guess, so we're scooching around like this. Yeah, that should work. Let's see if this works out. Got fuse over here. Maybe oh wait, that's going to that one? Why is that going to that one? Yeah, I guess I don't really care. Oops, wrong button. E is properties, whereas R is the one I was looking for. I guess we could go like around this one. It's got enough room in between. And then we still have the capacitor. Yeah, it seems odd that the power Ethernet controllers are going to like way on the other end of the board. That actually looks like it's closer to that one, but it's just one track. We'll just do it. I want to be done. I guess I don't care about aesthetics as much anymore because I want to be done. Yeah, we'll see if we finish this time. And if we don't, we're still going on to the other one next time around. Because a bunch of people are happy to see it. They're waiting very patiently for a full design. Okay, let's see. So we probably want to keep these relatively the same length. Because this is a diff pair, right? And these are going pretty high frequency. We're at 125 megahertz here. So that's a bit, right? So it's kind of hard to route these things though, because they're across from each other, which means that if you have an Ethernet chip which has crossover detection, then you can't really do anything wrong with these things as far as plugging them in the wrong way or mirroring them or anything, right? Which is an advantage to them being across from each other, right? But it also means it's hard to get them the same length. Yeah, this is just really not the same length. I mean, it's actually going to be fine because first of all, if we oh, I must be doing it at a different resolution this time because my measurement thing works. I'm not sure what I did. If you look at like this distance, it's 3 millimeters. If you work out, 125 megahertz at the speed of electrical propagation through copper wires on this board and whatnot, then it's still a small fraction of the wavelength. It will emit a little bit of, causing this skew will emit a little bit of radiation, like you will see it with antennas or whatever and near the wires. But I guess this is probably a good tip. The thing is, when you have skew, which means your wires aren't the same length, which means one signal gets ahead of the other one, right? Then you don't have the positive effects of the diff pair, right? Positive effects of the diff pair is that since one's going down and the other's going up, the sum of the two remain pretty much zero, right? And so first of all, you don't have to charge up the capacitance of the world around you as much because you are in sum still zero, right? So that's the capacitance of the tracks go down, but also the your emissions to the world also go down because there's not that much stuff that's changing voltage, right? From a perspective of being farther away, right? So if you do skew, then that takes away that. But there's another way to lower output radiation, and that is I think we got into it last time. Putting ground the layer directly under. So if you look at where I put ground here in my pore, ground is the next layer down. And so on a normal, typical board stack up, these are really, really close to each other. It's just like a thin layer of some plastic stuff in between, right? Or nylon or whatever it is. And so even if we have some skew, so right at the edge of the wave traveling through the board, there, the line going up is going up earlier than the line going down, or the other way around, right? If they're very close to ground, the ground plane, then you're also just moving charges around in the ground plane, right? Which is probably still not going to cause a lot of emissions, right? Because again, from looking farther away, you and the ground plane are still, pretty much same voltage, right? The way you can screw this up is like if I had a track going through here, which was, let me turn planes on so you can see how this affects the plane. So look, now I have a break in my ground plane, right? So the change in voltage, the wave traveling through this wire is going to get to here, and up to here there'll be a change in voltage traveling through or a change in charge traveling through the ground plane as well, right? And so they'll cancel each other out, but then when we get here, ground has to go all the way around, right? So then you're going to start seeing emissions, you're going to start seeing reflections and that kind of stuff, right? So under the wires that are going at high frequency, you definitely want to have an uninterrupted ground plane. If you do that right, you can screw a lot of other stuff up. You can get a lot of other stuff wrong, and it'll still be fine, right? So, that's my tip of being compliant even when ugly. Is make sure that the ground plane is right underneath your signal plane. I mean, if you have chips on both sides of the board, that gets harder, right? which is why you might want to go with like a 6-layer board at that point. A, uh, a power plane acts the same way. There's nothing really special about ground there. If you have a power plane, then you're going to be moving charges around in the power plane, and that'll cancel each other out in kind of the same way. But yeah, ground is. I mean, you typically have different power in different areas of your board, but you typically have the same ground everywhere. I mean, that's not always true, but at least on this board, it's true. I mean, I guess I left ground out for the area over here for the power plug going to the outside world, because we could be picking up, actual, bursts and lightning and whatnot over this. And that coupling into ground or spark gap distances and that kind of stuff, I didn't want to have to worry about that. And so that's why the ground is not going over that part of the board, but everything else has the same ground. Okay, so yeah, so we still have our TVS diodes to place. Oh no! See, that's why I was placing the TVS diodes first. Oh, so this is going to screw everything up. Maybe I'm going to put my TVS diode somewhere else. That's obviously dangerous. TVS diodes are usually priority number one when placing the routing stuff. But I so want to be done here that I think I'm just going to go like that. Oh no, that's not going to quite cut it. Yeah, we'll put it over here. So we're going to have the 48 volts. Oops, I wanted to do a really fat one, right? Because it's providing power to all the stuff. So just to remember to leave that space. Now, going back to electromagnetic compliance stuff. If I do this, what's wrong, right? If I do this, then there could be other things on this power track which don't aren't compatible with voltages over whatever, something like 60 volts. And if pin 15 just got struck by lightning or something, then we're going to have, I don't know, 2 kilovolts or something there. And then we're going to have that dropping down across the track to our transient voltage suppression diode. That means here it's going to be 60 volts, right? But that might not mean that it's like over here, right? Because we have a voltage drop in this line to get there. So we actually want to connect it something like this. So it has to go through the diode. U selects the whole track if you want to tear things up in KiCad. Took me a while to get used to that. I started on OrCAD. OrCAD was a buggy mess. But it was all that there was back in, I don't know, 1999 or 98 or whenever I started. Yeah, there was no KiCad. There was no old guy telling stories about before the war. Okay, so there's our fuse. And so we probably want to prioritize filter resistor over fuse. I don't want to get too close to that. Did I say filter resistor? Obviously, I meant filter capacitor. There's the filter capacitor. Oops. Oh, a lot of people tuning in on Sunday. Well, I'm very grateful to you, and sorry for screwing up your Saturday plans. Hope nobody didn't go out because they wanted to watch my stream and then I didn't watch the stream or something. I didn't stream it or something. I just realized one of the young students was like, if you are streaming every Saturday night, that's not very young people compatible. I'm like, oh yeah, did you notice I'm married with kids? So sorry about that. But I guess it's earlier in the day for the Americans anyway. I just picked the time slot by what I thought would fit around my family plans. So I'm sorry to everyone that doesn't fit so well into this time slot. Okay, this one I think we still have room to move this, or are we getting close? Let's see. So we got two diff pairs coming out there to go there, and then we got two that are going to have to kind of go around there to get there. So I think actually moving it to the left will help us more than anything else, because those are going to have to get over there. Yeah, maybe I should kind of, yeah, I guess it's kind of a chicken and the egg thing with putting these to where they do good TVS stuff, and then also making sure that we have room to route the diff pairs of the Ethernet, the RX and TX to get there. Wait, why is this thing over there? Well, we'll just put it up here and remember to scooch it. Those things are just all over the board. Sometimes KiCad does a really good job of putting components where they would intuitively should be. Sometimes it does just a terrible job. Okay, I think this is the last one on the chain, so I don't need to move it all around there. Okay, this is working out actually pretty well here. And that guy is some just stray random. Okay, this is for that. Wow. Okay, well. So here we got the fuse. We'll just put it like this. And then we can start routing some of these diff pairs. Let's go back to 2. I think I'm going to get into board stack up and board. Wait, am I too close to that? Why am I too close to that? Or are these a different width? Which width was I using? Oh, 1.5. Yes. Okay. Sorry. If you are doing things that are high frequency or like very delicate or whatever, then it's important to tell your PCB manufacturer how you want the PCB to be made. It's called the, wait a minute, sorry, I'm routing a center tap when I shouldn't be. You want to tell your circuit board manufacturer which it's called stack up, which basically means how you want how far you want the layers to be apart from each other and what kind of insulating material you want and whatever. Wait a minute, no, it wasn't 1.5. Okay, I'm just going to do these all new. And this is important because the wave resistance of a track on the board. Wave resistance is not like normal DC resistance. Wave resistance is a characteristic of the inductance in ratio to the capacitance of a line, and basically decides how fast energy travels through the line. And so you have some of the same wave mechanics in electricity that you do with water or sound or light or whatever, where if you go from an area with one wave resistance into an area with a different wave resistance, then you're going to have things like reflections and that kind of stuff. Which you also have, if you're thinking about waves crashing on the beach. If you want to be a good electrical engineer, then watch a bunch of waves, like actual waves on the beach. It doesn't all carry over, but it helps your intuition. So the wave resistance is going to depend on things like how far away the ground layer is. Actually, I could route that a little better to make them the same length. how far away the ground layer is from the layer you're routing on, for example, is going to change the wave resistance. And then also what material, like the capacitance of the polymer that's used to insulate between them is going to change your wave resistance. And I mean, you can get into all sorts of perfectionism and end up having to pay a whole lot for your PCB by trying to dictate this kind of thing. Oops, I'm going to have to scooch them. Or you can just look at the look at your PCB fabs stack ups that they have just kind of as standard, and out of that calculate, well, how wide do my tracks need to be and how far do they need to be apart from each other. And again, if you have like with these 2 millimeter wide tracks and just sliding them to the 2 millimeters I set up in the board as a gap, that's probably not exactly the right wave resistance. If this was gigabit Ethernet, I would have to be a lot more careful, right? If I wasn't in a metal box, I would have to be a lot more careful. If I didn't have a perfect ground layer right underneath them to catch all of my problems, I'd have to be a lot more careful. So, if I was doing something analog rather than digital, I'd probably have to be a whole lot more careful. Although that's not that common, but just in general, right? Like I don't know if you guys have seen the eye diagram, right? So if you look on an oscilloscope of your bits and you synchronize a bunch of them all on one falling edge of clock or something, then when they stack up on top of each other, it starts to look a bit like an eye, right? You have some of them rising at that clock, some of them falling at that clock, and then they rise again and fall again some later time. And basically you want the middle of the eye diagram to be empty, right? You don't want anything rising and falling like in the middle of a bit and those kinds of things. And as long as that's true, then yeah, you're going to be okay, right? So I did calculate out what the wave resistance is of 2 millimeter wide, 0.2 millimeter wide tracks with 0.2 millimeter gap. And I will have to, when I order the board, use a specific stack up. Tell them, hey, use this stack up. I think it costs like 70 cents extra or something at JLC PCB. It's insane how cheap they are. Yeah, do keep that in mind, right? We're going to get into that later, or you can find some other video on wave resistance and board stack up. I'm sure there's other people that have done a way better job than I can in live stream. Just for people that haven't come across this, because it took me a while in my career before I actually found videos, because I knew what to search for, right? As far as wave resistance, board stack up, diff pairs and whatnot. So yeah, I did. The purpose of routing on Saturday is to get your gut feeling a little bit calibrated, and also get you familiar with things you might want to know more about, right? It's not going to be a polished video on some topic. Yeah, okay, so we got these routed, and this is going to be some of the hardest stuff. So these are going there. That'll be easy. I just want to make sure that I don't get into the situation in the end where I don't have any more room on the board and have a bunch of stuff to still route. So yeah, these I'm probably going to have to put some of these diff pairs down to the bottom of the board, and we'll talk about that when we get there. But I would like to do as many as possible on the top, and with as little kind of going around places as I possibly can. guess I could have done that a little more gracefully to get both of them the same length. But again, a couple millimeters is okay. I think the wavelength in copper is something like 20 centimeters or 30 or something at this frequency with this stack up. I mean, depending on your wave resistance, you're going to have a different wavelength, right? So you have a different traveling speed because the wave traveling through the copper has to charge all the parasitic capacitance along the way through all the parasitic inductance along the way, right? So depending on how much parasitic capacitance, parasitic inductance you have, it's going to take longer or shorter to do that, right? Right. Yeah. Okay. So yeah, I mean, but gut feeling, it's definitely not the speed of light. It's definitely a lot less than the speed of light, right? Okay. So this guy's going to definitely have to go under the board. So going back to, I guess I could actually go over and then just do a little bit under the board here. I mean, going back to what I was saying earlier about leaving the ground plane intact. We definitely don't want to go through the ground plane with these wires. I think we're just going to go all the way to the other side of the board. It's definitely also good to switch sides of the board very close to each other, right? So vias like that. And that will be a slightly different wave resistance, right? Because there's, the vias are definitely thicker than a track. I mean, we could go super pedantic nerd and calculate out like how far apart the vias need to be in it. I mean, if you're doing something in gigahertz range, you definitely have to do that, right? Like you have to calculate, well, okay, well, how are the vias made by this manufacturer? How do I need to, how far do I need to pull them apart so that I don't have, a serious change in wave resistance? Because yeah, you're going to get reflections the same way you get reflections with changing speed of light in different mediums, right? I mean, that's why a mirror reflects, because you're going through different mediums that have a different speed of light, right? There's a very good Veritasium video on that if you want to check it out. I don't remember the name of the video, but it's something like light speed Veritasium or something. Should find it for you. Okay. One could also say that I probably should leave like a gap of ground in between the two diff pairs, like the RX and TX diff pairs. And that would probably also be true. But I don't know, I have them switched around here. I guess that'll still be fine. The Like there could be a little crosstalk between them. I mean, it'd probably be better if we had ground in between. On the other hand, 100 megabit Ethernet, I mean, that it worked at those frequencies back in the day before we had the quality of copper in the circuit boards, before we had like people don't realize you can actually tell which direction a track is going across the board just because of the weave of the uh, carbon fiber in the I mean, most circuit boards are like carbon fiber and then some epoxy to stiffen it, right? And since the carbon fiber and the epoxy have a different capacitance, right? You can actually tell whether you're going like diagonally across the board or straight across the board uh, with a VNA, like if you're doing frequency tests on your tracks, like that used to be, when circuit boards used to be, not as quality controlled, that used to already be a problem, right? So like, back 25 years ago when 100 megabit Ethernet was relatively new, um, you had all sorts of other stuff messing with you, right? It used to be hard. it's it's not as hard anymore, right? Like, make sure you got a ground layer underneath. Make sure all that stuff is good, and then yeah, it'll be forgiving. Um, like, I've put a whole bunch of stuff through compliance testing so far, and they actually test your emissions, and they test. I mean, I guess they don't test crosstalk, but we have tested crosstalk with lab equipment, and it's yeah, like it could be better, but if better is like 0.5% better, then I'm not putting effort into it. I mean, if you look at boards that other people made and products that you just bought, right? You're gonna find a lot of a lot more egregious stuff than that. I mean, we're certainly way above average in our sort of board quality, I think. A lot of people don't understand the voltage drop on the TVS stuff. That's going to be quite common. Let's see. So do I actually want to go under it? Because I mean, there are magnetics in here, right? Um, and potentially there could be some crosstalk based on inductance from them. And they are usually shielded around the outside, but not down towards the board. Uh, yeah, I think I'm just going to go up and around, just just to play it safe. I mean, yeah, it doesn't really matter at the end of the day, I'm pretty sure, but just because I don't want to have problems, let's just go up and around here. Okay, those are, oops, no wait, I'm dumb. This is the other one. Oh, these diff pairs aren't quite working out. Oh yeah, because we're approaching the chip from different angles, right? So they're going to be switched around depending on that, but it's okay. We can still do something like this, right? Where we go up and around. Again, at a gigahertz, I would be a lot more careful, but this is going to be fine. Make the tracks on the top and bottom also somewhat the same length. And here, yeah, I mean, they're still not the same length, but just by a little. I mean, it's like I've seen designs from we kind of have a philosophy of letting people do things wrong and then see what happens with their first boards, and we have a lot of student labor and whatever. And so yeah, there've been some boards that I've seen that have definitely been egregiously worse than this, but would still pass EMC because they got the ground layer right, right? Like that is so important. Yeah, this is probably almost like watching people mow lawn or something. Me rooting all this, which is why I decided next week, executive decision, even though the poll said let's do another switch. That's so much redundant rooting. So we're doing a sensor, doing a temperature sensor, beginning to end. I mean, I would like to root the industrial switch at some point, but figure I don't scare away my 80 people or something that watch me at this point. It is growing. Thank you guys for telling other people and retweeting and whatnot. I have absolutely no idea what I'm doing as far as streamer influencer stuff. I do what I know what I'm doing with PCBs. So thank you for whatever you've been doing that is making this more popular. It seems like we get about 10 people more each time, and I'm happy for that. Yeah, I kind of told myself, well, I'm going to do 10 episodes, and then depending on how many people actually seem to be getting value out of it, I'll decide after that. And so if we keep getting 10 more people every time, then it's probably going to be more than another 7 episodes, because I certainly will not run out of things to root. Oh wait, we're really egregiously not the same length here. Yeah, why don't I just kind of curl around and come from the back there. I mean, you also definitely, well, not definitely, you also probably don't want to make things go around in circles too much either because of the inductance, right? So we're kind of striking a balance of making the tracks the same length versus parasitic inductance. It's fine. It's fine. Okay, with this one, I think we're going all the way around, right? Yeah, okay. Oops. Oh, wait, this is switched around. Oh, wow. So do I go vias underneath? Because like this is going up top and the next one's going to actually go lower. So if I was a perfectionist, I would probably switch these around. The diff pairs, just, yeah, switch the diff pairs around because the chip has crossover detection. So we could also do it the other way around if we were a perfectionist. But I think we just want to get this done. And this is actually fine. Notice that I'm going all the way through to the other side of the board. First of all, because the wave resistance is going to be similar on similar layers, as in top and bottom are going to be similar as far as wave resistance, whereas the middle layers are going to be a different one. They're usually a different thickness of copper, for example. Like if you go with just the plain vanilla defaults JLC PCB, then you're going to get, I think, what, 35 micrometers on the top, and then 15 point, whatever half of 35 is, 15, 17 point, whatever, on the in the middle. So they're half as thick, which means they're going to have definitely a different wave resistance, right? And also they have polymer on top and below them, right? Whereas on the outside of the board, you have polymer just below you, right? I mean, I guess you have like the solder mask on top, but that's a different material. And so, yeah, so we're prioritizing like for like over distance through vias, right? And because we're going all the way through, if we turn the fill back on and update it, we can see that the blue ground is still going completely through, right? The only gaps are the vias, right? Which, if we had a bunch of vias, that could also be a problem. Like you do have to watch out for that. Splitting up your ground plane based on or because of vias. So that's not to be ignored, but here it's fine because they're the only vias around. So yeah, it's better to go all the way to the other layer rather than going through middle layers because you're, I mean, having the wrong wave resistance on diff pairs is still better than having different wave resistances along the way, right? So if you have the wrong wave resistance all the way through, then you have 2 points where you switch from the cable is probably going to be the right wave resistance if you don't buy a cheap one. The connector is definitely going to be the wrong wave resistance because it's just it's a bunch of pins that was standardized before anyone thought of putting Ethernet through it, right? So it's definitely going to have the wrong wave resistance. And then once you get to the board, then you already have one transition from whatever the connector's wave resistance was to whatever your board's wave resistance is. And so even if you're a little bit wrong, it's better than being non-consistent, right? Because yeah, I mean every time you switch wave resistances, you're going to degrade your signal some. Yeah, next week we're going to do a design with USB, and there we're going to have to be a little more careful than here. Although I think it's just slow USB, so it's actually not as high of a frequency as this here, but it's also voltage driven. This is, current driven, right? Um, we're 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 moving current around in the coils in the oh no. Let's see. So I guess I do want to go in through here. Like that. We'll see how the other one turns out. Yeah, so we're moving energy around in the coils uh, rather than doing like voltage to voltage and then with like a terminator or something, right? Which we're doing with USB. There are no coils with USB, so it is a little bit different. Yeah, there's a bunch of gotchas with USB that we'll go through next week. USB actually is also pretty tame because, I mean, generally, if it's something that people have been doing for a while, at this point it'll be tame because we have better circuit boards and better CAD software and better knowledge and all that. Am I going to go all the way around or am I just going to V it? I'm going to V it. Let's see, but where do I want to? I mean, I am busting up the ground layer with my vias. So, yeah, we'll do it something like this just so that we don't mess with that one so much. And yeah, so if a technology has been around a while, then it's going to be somewhat robust just because it used to be harder to do things. So super speed USB, well, okay, you got to be careful there, but things like the normal high speed, full speed USB is still not really a problem. I mean, it's kind of unintuitive that high speed is actually faster than full speed, and that full speed's not the fastest. But marketing, right? Uh, so yeah, so full speed USB is what 12 ish megahertz, and then might be 12.5. I don't remember off the top of my head, but something in that ballpark, and then 480 for high speed. 480, I mean, that's getting up there where you have to be careful. But yeah, I think our design is just going to be the full speed, the 12, because we're going to be using a Raspberry Pi Pico microcontroller, and that doesn't have the high-speed USB, which is a shame. The connectivity frequency is probably my only real gripe. I mean, the ADCs, yeah, they screwed that up, but that's okay. You can just use an external one if you really need a good ADC, which you often do. So you often need an external one anyway. But yeah, the tool chain for the Raspberry Pi Pico, however you pronounce that, microcontroller is actually really good and modern. Okay, so am getting into some space problems here. So how about we rotate this guy over here? So we still have the same power integrity because it's actually maybe even better power integrity, right? Because our power loop here, you know what I'm talking about. Go back to last episode. Our power loop here is going from the ground of the chip through the power, through the capacitor and then here. So our loop actually got smaller by me moving it over there, right? We're gonna have to definitely remember to put all the vias in next to the right pins there. That's a common mistake that I've been known to make. Get everything placed optimally for perfect power integrity, and then forget to put the vias in the right place. But yeah, once we get this rooted, then we can go and do that because otherwise we'll be done with this chip. So we got some space now to work with. We'll see if the gods are nice to us. I guess not really. We got the same problem going on here again because either we go around the outside, in which case those work, but then we'll be the wrong way around as far as the diff pair, right? But if we do it like this and then do one underneath, that'll that'll actually help us with our space problem too, because we can move this away from that one, and we'll just go along the bottom for the same stretch. Get a little bit away with the vias, because they do, I mean, those holes in the ground there will actually affect the rate resistance at that point. Just a little bit. I mean, not enough for it to really matter, but which one will be above or below? Above. Okay. Yeah, it's nice to get back to this compute module industrial switch thing. This is gotten some good mileage out of this product, and so we're, yeah, I mean, the redesign here is for better manufacturability. You know, got some components that are updated. Got the, you know, making everything ceramic capacitors, getting rid of the electrolytic capacitors, because we'll certainly extend the life of the thing. Also, yeah, putting it in a sexier box. It used to be in a kind of an ugly box, even though it still worked. And then we designed like the custom cut aluminum, like CNC cut aluminum. It's gotten so cheap at this point that basically the bottleneck to oh, that's going to the LGA, which I haven't done yet. It's not in the circuit yet, I think. So we'll just leave that out for now. Okay, here we got SCL, SDA. So that's also going to the LGA. So I think we're good. These are all, oh yeah, these were the LEDs, which we're not using because we're in a metal box. No space for LEDs. On the other hand, it's waterproof and dustproof and rugged and all that kind of stuff. Okay, so we got all the diff pairs routed. Then why don't we do the power stuff here first, and then once we got that all squared away, then we can do how we're doing on time. We might finish. Probably won't, but that's okay. You guys can picture me doing the rest. Yeah, we definitely. I definitely haven't put in the LGA yet. LGA stands for Land Grid Array. Basically, if you want to put two boards on top of each other, then you can make, you know, on the one board you make pads, and on the other board you do castellated holes, is what they're called. It costs a little extra, but those are the holes that are like on the edge of the board, that are like halfway cut off by the side of the board. It's like the little notch thingies. You see them on a lot of dev boards, like the Raspberry Pi Pico board has castellated holes along the sides of it, right? So yeah, so you do one board with castellated holes, and the other one you just put SMD pads, and then you can just put the one on top of the other, and then solder across pretty easily. And yeah, I mean, you theoretically can also actually have a pick and place machine, you know, place the LGA board on top of the other board, you know, the piggyback board on top. But yeah, we're still going to be doing it by hand. I mean, we're not doing tens of thousands a year yet. I think I guess we have done products that have gotten that big, but we did them out of house, that kind of stuff, right? Oh, wait, why am I too close to other things? Oh no. Let's see. Because we do need to get a via in here, because we want the via close to the capacitor rather than close to the pin. Otherwise, you know, the pin's noise could be going around. I mean, it's the same voltage drop thing, but in this case, it's not resistance. It's more magnetic resistance. But yeah, we can get into that. We got into that last time probably enough. So if you don't understand why I'm putting the vias close to the capacitors, then watch the last two episodes. We got into that a bit. Let's see, so this looks fine. So I'm using this lower middle layer, so not the one below the chip, the next one down, to route the power here. And that usually works pretty well. If you have the power decoupled pretty well, you don't really always need a plane. I think I probably am going to use a plane here. I guess the question is which areas. Yeah, I'm definitely going to do a plane here just to make sure that everyone's got good power. The question is whether I, so the most critical is probably the 1 volt, right? Because that's what the core of the chip is running off of. And so if we have too much noise happening on that, then we're going to, screw up the chip internals and drop packets and whatnot, right? Why wasn't I able to do a VIA there? Okay, there we go. Got the VIA. So yeah, so you want to be like prioritizing based on, what would go wrong if we do have a power glitch. And the core of the chip is pretty dang high on that list. If we have a glitch on like the I/O, then okay, maybe we will screw up a couple of bits and have to resend the packet via TCP. At least if it is TCP, then whoever's sending the packet is going to retry, and it'll all be fine, right? But if we screw up the core, then the chip might crash and need to completely reboot or get into some undefined state or whatever, right? So that's high on the list. So we're going to do, okay, so is that all that's at this 1 volt? I think so, because the chip is making this 1 volt via a internal LDO, I think. Yeah, I don't really see an inductor here, so it probably is LDO. You can actually look in the schematic. There's the 1 volt, and there's a ferrite bead to 1 volt analog. So yeah, no, there's no inductors here. So yeah, I have seen, like, I have a design with a gigabit chip that definitely does like it's got a buck regulator built into the chip, which is kind of wild, but you can tell these things were made to be really cheap, right? So it's all in one chip. But here, yeah, it's got to be an LDO that's dropping the voltage down somewhere in the chip. And so this is the whole power net. And so I want to make a plane that encompasses all of these vias so that we have like good power. Wait a minute, what am I doing here? I want to be on that plane, and I want, oh yeah, I was using the wrong tool. That's why I was acting weird. So I want to be, yeah, on that layer, and I want to be connected to 1 volt. So yeah, defaults look good. We'll just make it some weird polygon that connects all the vias together. And then we'll have excellent power integrity. Yeah, making sure that your power loops on your capacitors are good, and making sure that that including the ground side of things into that equation, and also making sure that your vias connecting, one capacitor pin pair to another capacitor pin pair, that they're close to the capacitor. If you do both of those things right, then your power integrity will probably be fine, unless you get into some really wild stuff. But this is definitely not wild yet. People were able to do this 25 years ago without any of the knowledge in CAD and whatnot that we have today. So it's not too bad. Let's see. So what other nets do we have? Got the 1 volt analog. Okay, what are, oh wait, we got another capacitor that's on that same. Did we forget something? Oh no. We have so much rooted already. I guess, yeah, okay, we got the 1 pin decoupled well, and then we got the ferrite bead, so I think we can just put this guy, I'm going to put him over here so it's easier with the silk screen. Yeah, just to stabilize it once it comes in, and then we'll put a via here, and then go, yeah, I think we're just going to go around the outside with that after we do the other nets. So what other power nets do we have? Here we have our 3.3 volts. And I think that's some core something something. I'm not quite sure why they do V and VA for the 3.3, but VA is probably going to be the driving pins. So we'll do that last because that's going to be the noisiest and probably the least important as far as integrity, just because, you know, we don't have huge problems when we screw that up. So let's don our fat track. We're making fat tracks, yo. There we go. I'm just gonna connect it like around to each of the vias, and then want to make sure we're outside of those vias. Oh, I guess I already did that with tracks, so we can't actually screw that up. Bup, 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 bup. Yeah, guys, feel free to drop comments of like what level you're at and whether I'm meeting your level or whether I'm going too fast or glossing things over or anything like that. Um, yeah, I mean, my goal here is to spread some knowledge, and so depending on what you guys want to see, that's the level I'll be aiming at. Oops, I want a D rather than G. I think I'm going to pull these down and so that I have a little more room here because I'm not going to be able to get a via in there. And I don't want to mess with those diff pairs. Okay, so now I need G. Because G will move the tracks for me and show me anything, any design rule check violations I'm making along the way. Shortcuts in KiCad are basically like, I don't know how many of you guys work with the terminal. It's basically the terminal, but for routing, right? It takes a while to get used to, but then you get really fast using the shortcuts, the keyboard shortcuts. Let's. Oh, I got some weirdness going on there. I mean, again, it doesn't really matter, but my mind wants to make it nice and straight things like that out. Yeah, so I'll connect those when I do the land grid array. Okay, now I should theoretically be able to get a via in here, I think. Oh, no, still not. What do we do? What do we do? I guess I could also do this guy. And then have room for the via there. Again, we don't want to put the via in the pad because then we'll have to buy the more expensive plug vias. And if we put it in the pad and we don't pay for the extra plug vias or tented vias, then we're going to have the problem of solder paste when it gets, in the solder process. There's a hole in the pad where the paste can run down into. Then every now and then you're going to have the problem where, the paste runs down into the hole rather than connecting to the chip, and then you're going to get soldering errors. And since you don't get them all the time, that's a nasty error to have. Because it might work on the prototype and then not work later because you missed it on the prototype. Yeah, so, and they are, plugged or tented vias are definitely more expensive because it is more work for the PCB manufacturer. So if you can get away with putting the vias outside of the pads, then by all means do it that way. It's cheaper. If you can't get away with it, well, the technology's there, right? Like if you're routing the Tesla self-driving computer or something, then by all means put the vias in the pads and just pay for the extra tenting. But on this design, maybe save us $1 a board or something, which does add up, right? Like, we do ship a lot of boards, and yeah, it actually might be more than $1 a board. I mean, it is. I mean, especially considering how cheap PCBs are at this point, right? Where it's like, the PCB itself without tented vias might be like $2 and it might be $3.50 with tinted vias. Like that's definitely a difference, right? Um, okay, so we got the 3.3. Is it going to anything else besides that? Okay, why is it going? Okay, well, it's going to that because that's um, our regulator stepping us down from 5 volts. What else was it going to? Oh, okay, yeah, it's going to the power over Ethernet controllers. That's also logical. They need 3.3 volts to do stuff. Okay, so now we're going to do the analog part. We're going to do it inside. No, we're going to go around the outside with the analog. So I guess we want to do this. Goes down, so we can do the analog. Those guys, yeah, they can scooch. That's clock. Another reason why I already gave the tip last time. Can't repeat it enough. Name your nets. I mean, I can see here without even seeing the crystal up at the top that these are, XI and XO is always crystal. So yeah, if I hadn't named those, then I wouldn't know what that net was, and I wouldn't know if I could scooch it or any of that kind of stuff, right? Okay, I'm probably gonna have to go around the top late. Oh wait, that's the whole VA. Okay, well that was easy. Okay, let's switch back to point 2 and make sure. I guess those are already connected. That's do something like that. Yeah. Although actually, come to think of it, that's actually probably a better design because then we don't have the noise of potential noise of those going into that. I mean, it doesn't matter. We're splitting hairs there, but just to be endlessly pedantic, or if you were to be endlessly pedantic, then that would be important. Okay, I think we got most everything ready. What are those tracks? Oh, those are going to components way up there for some reason. Yeah, we didn't really do a very good job of placing these. So where are these actually going? Oh, okay, so these are the center tap decoupling. So this is a good way to keep noise off the lines. If you have the center tap of your magnetics decoupled to ground, then whatever skew or offset or whatever you have is just going to get swallowed by the capacitor. That helps the compliance side of things. And we could very, very probably get away with not having these. I mean, we made the connections pretty close together anyway. But, I mean, back in the day where you had to do 2-layer boards and whatever, you're definitely going to have a lot more skew than we can with the 4-layer ones. So, yeah. On the other hand, capacitors are dirt cheap. I mean, these are probably like less than 1/10 of a cent or something. It's insane how cheap components have gotten. People don't give the Chinese enough credit for how much, I mean, it's not just the Chinese, but Asian manufacturing in general, by how much they've driven down price on this kind of thing. It's insane. I mean, you're buying a roll of like 10,000 chips of something, and the roll cost you like $3. That is just utterly insane to me. I mean, calculate that out. What fraction of a penny the things cost, the single parts. I mean, it's more, at that point, it's more expensive for the pick and place machine to put it on the board than it was to buy the component, right? Like the solder on the pads is more expensive than the resistor. I mean, holy, yeah. Okay, so yeah, so here is one of those things where I could really easily forget the via, and the board, like design rule check, wouldn't tell me, right? So that's a common problem. And you do want the vias like really close to the capacitor, because whatever you're decoupling against might be coming on, or it's probably coming on some ground plane, might not be the top of the board, right? Okay, so where do these guys come from? Oh, these are from that one. So I'll just put them here. There will be some that'll be harder to place at some point here. because I know I didn't leave a whole lot of room every time for the decoupling capacitors because I didn't have the room. Okay, so we're going to scooch those on in a minute here. Let's finish up the actual Ethernet part of it before we get to the power of Ethernet part of it. Okay, well this is still going good. Ergonomic here. I mean, I guess if we were like really pedantic, we could like spin these around the side. Although I guess, yeah, we're decoupling to this ground, which is like the ground path underneath the two wires all the way back to the ground of the chip. It's probably kind of the, what we're decoupling against, right? Because, if there's a difference in voltage here at the center tap, then it's going to be coming from some asymmetry in the diff pair, right? And so that asymmetry in the diff pair is going to be traveling across as a charge in the ground plane along with the wave. And so yeah, and then each side of the diff pair goes through the inductor, and then the center tap should remain 0. And if there's a skew, then it won't. And so yeah, we'll be decoupling that, closing the loop, as it were. Yeah, but yeah, you could get away with not having those components on the board. It's mostly just for peace of mind at this point, and not being your fault if it doesn't work, right? Like that's the thing, especially in a contract development case. There's a lot of human issues, and one of the human issues, like if you screw up something completely unrelated, and somebody then takes a look at your board and like, why did they screw this up? And they see, oh well, they're missing these capacitors. It's like, what are you going to show them your VNA test that they weren't needed? Just put them on there. They don't cost anything. Okay, yeah, well, I guess that one we're going to go around the outside of the board, which is lengthening our. Oh wait, did I grab the wrong component? Well, yeah, I did grab the wrong component, but oh well. We have the exact same thing I wanted to say here too. So yeah, here we're going around the outside, which is making our line a little bit longer. But on the other hand, these are mostly just for the peace of mind of the customer who looks at them. I mean, I guess, yeah, I don't think we're using the most expensive magnetics. Like if you want the best ones, probably like Rüth or Worth is how people in English pronounce that German last name. They have some pretty good magnetics that are wound by machines, and therefore tolerances are just insanely tiny, and they do cost more. So if we were using like Worth magnetics here, then I would certainly say you don't need them on this side, because the other side, the power of Ethernet side, well, that side, that's actually going through wires that we don't control, that are wires outside, where the cable manufacturer could have been cutting corners and whatnot, right? But this side of the magnetics, which is our center taps for these lines, like, yeah, if it's a worth thing, then don't worry about it, right? But since we are using some Asian magnetics on this thing, because they're also good, right? But I mean, the problem with some borderline no name, like not actually no name, but borderline no name Asian magnetics is they're usually wound by hand, which means no two magnetics are exactly the same, because they're by hand, right? So somebody's actually pushing the wires through there, and so the coils might not be symmetrical, right? So that in that case, this decoupling capacitor will also help us swallow the noise, right? So yeah, but yeah, at the end of the day, they don't cost anything. So yeah, I mean, the main cost is putting them on there to begin with. Okay, so we do want to be connected to that, but afterwards, wait a minute, let me make sure I understand how the wires are going to this thing. Yeah, we're going up through there. Here we're going to there, and then to there. So our decoupling cap, I guess we could just do this. That'll be fine. And then the fuse can go like here. We definitely want to make sure and not like route it from here somewhere, because this is, you know, not yet. I guess I'm kind of beating a dead horse there, but I've seen that problem so many times. Yeah, like when people fail EMC testing, it's almost always something like that, where somebody just put the track wrong. Yeah, or they didn't have a good ground plane. I mean, those are the. Yeah, it's also a good tip. Like, go talk to your EMC testing lab. Like, they will offer. Oops, I'm in the wrong size. They will offer you to just do it, where you just tell them what needs to be done, and then they'll test it all without you being there. You know, they usually have guys that'll be able to get your chip running with a small tutorial and whatnot. But if you do it that way, if you don't show up and for the in person, then you won't be able to ask them all the questions about, like, why do most people fail, and what's the wildest thing you've seen in your career, and that kind of stuff. I mean, those guys are just treasure troves of indigenous knowledge of why things don't pass when they don't pass. And that's probably why I have such a good track record. Is that I've gone to the first couple and just talked the guy's ear off, and just well, what about this bus? What kind of failures do you see there? What about this bus? What kind of failures do you see there? And they're happy to do it, right? Because they don't have anything to do while the test's running. They're usually glad to have someone to talk to, right? So yeah, that's definitely a tip. If you have the chance, then go to the EMC testing lab next time product gets tested and just talk to the guys. Okay. Yeah, this really has to go there, so I'm just going to start scooching all of these guys so that I have room. When I could put it somewhere else. Again, they're not that important. But on the other hand, it's not so hard to scooch all these guys. By the way, sorry to the non-English speakers, scooch is actually not a word. At least not like a proper English word. It means to slide something. I should stop using all sorts of weird dialect slang words when talking to an international audience. I'm sorry. Yeah, I was very pleasantly surprised to see how many people from Africa have been tuning in. I didn't know I had fans in Africa. I mean, I guess I did know from the C++ stuff that there were some, and I've been wanting to actually go to some of the African user. I guess that people that just know me from PCBs. I'm also somewhat known in the C++ world, although I haven't really been tending to that as well of late, because I've had to ship hardware and debug hardware things, and yeah, software's actually been working pretty well recently. So I kind of go where the fire is. But anyway, I've been wanting to actually go to some of the African user groups because, yeah, I find it cool just how many people there are there that are passionate about C++. I've been seeing them all on X and stuff. And I've never been to Africa. I've been all over Europe and over much of the US, and I've been some places in Canada at least. But yeah, I haven't been to Africa yet. I know a lot of really nice people from Africa. So, yeah. Hey, guys and gals. Thanks for being my biggest stream demographic, surprisingly. if you feel free to comment either on X or on YouTube or whatever. I will try and read the comments if you have anything specific you want to learn or whatnot. We definitely have a lot more streams to go, and I can talk about whatever you guys want to hear about. Let's see. Okay, so we just have the PoE stuff. So these, I guess well, I guess they kind of do need to be. So we need it to be a little skinnier, I think. Let's see how this fits. I mean, all of these components are short. Oh, this fits actually pretty well. All of these components are short, so they can definitely go under the plugs. So I did kind of move these around to where they kind of work already last time. And so they do kind of work out. Wait, what? Okay, I do have to worry about ground here. Let me look back at the schematic because there's some serious like ground sensing stuff going on here. Let's look at the schematic so you guys know what the hell I'm talking about. Okay, so here at this point, it's important for the chip to know what exactly the voltage at that point, including all sorts of voltage drops and whatever, because it's measuring against like pin 18 and 19. It's going to be measuring against each other, right? And by the voltage difference across there, it's going to know how much current is flowing through the transistor, like Q7 here. So the current flowing through here is going to cause a Verizon voltage here, but only a little bit, right? Because we got half an ohm in parallel, right? So we're going to be at a quarter ohm, and a quarter ohm is not much, right? So if we have some ground offset due to some noise or something, then it's going to be problematic here. So let's look at why did we have ground here and here, and which one is the right one? So that's pin 7 and 11 of this chip. Which one was the sensing one? 7. Okay, 7 is digital ground. Okay, so we don't want to route it the way we routed it here, right? Because digital ground is going to be potentially noisy, and we want to sense the ground at this point, right? So I'm going to put the God vias here. Sorry for anyone who's religious. I don't want to be what is it? Gotteslästerung in German. What is that? Blasphemy? Using the Lord's name in vain. But if I say master via, it's going to be another set of people that are going to be all bent out of shape. The main via. Yeah, I think we should just treat people better rather than use different words. But anyway, okay. So here we're going to be connected to ground, like at one point, and we're going to be sensing that point. So we need the tracks to be big so that we don't have big voltage drops in the tracks. We definitely don't want to connect ground, digital ground in there like that. So here we have all of, we have one channel resistors coming down to ground, one channel resistors coming down to ground. That's all going to be connected to the ground layer here at these vias. And then here we have our sensing line, right? And we want to make sure that this doesn't connect to the plane, because I have a ground plane on the top. So do I do a keep out, or do I just do it like a cheapy? Where is this track going? Okay, this track is going to go all the way around. I think it's going to go all the way around. So I could just use that track to get in the way of the copper pour, which is, maybe dirty, but does actually work well. So this is digital ground. So with digital ground, we're just going to go to ground plane immediately. This is probably what's going. Yeah, okay, here's digital plus. I mean, the thing is, with the power integrity of this chip, we don't have anything that's high frequency on this. Like I squared C at 400 kilohertz is like the highest thing. So yeah, you know, your power integrity as far as that kind of thing um, only needs to be uh, perfect for the high frequency chips. Now we are switching loads here, which can cause, you know, some power integrity issues, but we're actually switching them through resistance and far away in these MOSFETs. So yeah, the fact that this decoupling capacitor is not like right between the ground and the, you know, the digital ground and the digital plus here doesn't matter at all, really. I mean, you know, do it as best effort, obviously, right? But if our chip is running at like 400 kilohertz or whatever the I squared C is, you know how much difference there is between 400 kilohertz switching frequency and our 125 megahertz? Like that is worlds, right? Like how much bigger the loop can be here and still provide like the same, yeah. It's yeah, so it's fine. So we don't really have to worry about that. So wait a minute, why am I? Oh yeah, okay, I get it. That goes. Guess maybe I could use thicker wires for the actual powery stuff because with this MOSFET we're basically switching here the collector to ground, right? Um, oh wait a minute, are we switching this? Yeah, oh, I'm sorry. So this is the gate. So pin one's, yeah, it's even on there, right? Gate 3. Yeah. Good thing we labeled it. Odin just can't read. Okay, so here's where we're going out with power to the fuse there. And that's probably enough of a track. Like we're going to actually only see, what, 200 milliamps or something? That track's thick enough. I mean, it's kind of, you know, a little bit sort of, okay, so this is just sensing, so we don't have to make this fat. We didn't have to make that fat, but oh well. Okay, so here we have the gate. And so the gate has to go all the way around. So I'm just going to use the gate to block out the ground plane from coming up in here. I guess I could go like that. Now that's actually dirty. Nah, maybe I do want to do a keep out. Ah, okay. I'm sorry for being dirty. Let's see. So copper keep out. We just need enough to, yeah, it's on the front. We just need enough to make sure that ground plane doesn't connect here. That should be enough. Okay, so let's look at the ground plane to see if it's actually doing it right. Oh no, did we do it wrong? See, here's the problem, right? We have the ground plane connecting in through here, and so we're going to be sensing whatever's going on here and not what's going on up here, which is what we want to make sure we're doing. So why did I do the copper keep out wrong? Keep out tracks, keep out vias, keep out pad. Keep out fill zones. Okay, now the B key refreshes that. There we go. Okay, so this is what we want to do. Make sure that there's no ground connection here, because otherwise we'd be messing with the sense. Because like, you know, what if there's voltage drop between this point and, you know, this point or something, or over here? Then we're going to be seeing that in our voltage sensing, because yeah, it's going to be part of the voltage drop across here. So that's why we don't want to connect ground here, because it's our sense line. Same would be true if this, you know, this ground island here was going other places. Then we would want to make sure that that's not true either, or that, yeah, that it's not connected there either. And we could actually make that island a little bit smaller like this. That's probably also a good idea. Yeah. Okay. So look, how are we doing on time? Yeah, I guess we're not going to actually finish today. So why don't I do representative things of the stuff that we still need to do? Okay, so that's gate. So that's the actual switching. Let's turn off the fill zones just so we don't. Yeah, okay. Yeah, if I had time, I'd probably go into the schematic and make sure that the switching, make sure that the lines are, the PoE lines are going to the connectors near the chips rather than all the way across the board here. At some point, yeah, maybe I am going to do that in post, make them in a logical order. Well, I guess it doesn't matter. You can always fix it in software. Since the PoE controller chips have an I2C bus, and over the I2C bus, you can actually turn the ports off. One application that I have wanted in a Power over Ethernet switch for a long time was to be able to talk to the switch over Ethernet at some address and tell it to turn its ports off. Not just to be able to turn them off, but especially to be able to turn them off and then on again, right? To reset the device on the other end of the line. That would be incredibly cool. And I have built one as a like dirty prototype. I just haven't made it a product yet. So yeah, this board may get to the point where that's true, which means it's going to be confusing for whoever has to tell the I2C which port to turn it on and off because they're all jumbled up right the way it is now. But yeah, I'll fix it in software. Okay, so I2C, that doesn't really matter because that's, I guess I could scooch this guy down a bit so that vias will fit underneath. So let's see, is there anything else that we need to talk about before we run up towards the end of the stream? So here's where I'm making 3.3 volts out of the 5. Put that on the board. And then this, yeah, this is just the same circuit again. Yeah, so I'm just going to keep on routing here. I think we talked about all the important stuff that there is to talk about with this board. Yeah. Same thing here. Going to do the 2 vias. The ground. Oops. I'll just, oh, not G. I want D. There we go. You can see how G and D differ in their dragging algorithm. Okay, let's switch to the small track just so people know what we're doing here. Wait a minute, which one is the sense line? 22, wait. It selects the last chip you clicked on, so in that case it was the LDO. So now, oops, I forgot to remember which pins it was. 22 and 23, are those the sense lines, or which one of those is the sense line? So 22, okay, 23 is strapping wire. That basically changes its address on the I2C bus. So the sensing one is actually 22. Yeah, the strapping one's not going to be noisy. It's going to be okay if we connect those, I think. Or if you want to be really pedantic, you'd have to like make sure that those two are different. Although I guess we could do a keep out, like a zone keep out here. Get really fancy and say something like tracks are fine, vias are fine, pads are fine, but pores or fills. Didn't they used to be called pores? Anyway, I guess it's fill now. I should say it the way KiCad defines it. We could just do a ground keep out of like this. This is going to look odd on the board for people. But nobody looks at boards anyway, right? Okay, so if we go B refreshes the fills. Look, I said it right. Okay, yeah, that's looking good. So we, well, 22 was the right one, right? Yeah, 22. So 22 gets connected to this. 23 gets connected to that. And we're all good. Yeah, that keep out worked out well. Keeping stuff out. I shouldn't have wanted to do it dirty. Oh, so we only have one decoupling cap? Well, as I said, at this frequency, power integrity is going to be very forgiving. Yeah, that's the thing with the gut feeling, right? Like sometimes I see people doing like on a chip like this that's, you know, not power integrity susceptible at all. Will do everything perfectly as if it was some high frequency chip. And then where it really counts, they won't. Okay, so we got decoupling here. So yeah, we probably should do to ground there. And then we'll go on to 48 volts there. So let's just go underneath and put up here. This is just so that the chip has a a reference to what the upper voltage is. It's not going to be pulling a lot of power over that. We put a via here. I mean, again, that's just strapping. And then this will be probably some power supply thing. So I can go in there. And we do, wait, where's this one going? Oh, okay. And where's this one going? Oh. What was I thinking when I set this up? I mean, there, we could do something fancy like that. But that's not going to work for that guy. So I guess we're just going to do some board side. Oh, I guess I could go around the other side. I guess that's still not going to help me all that much. Well, that's what VIAs are for, right? Again, I have no idea why they are exactly where they are, but I don't really have time to deal with it right now to make it pretty. Boards tend to work even if they're not pretty. It's just for aesthetics. So it'll be fine. I mean, things like this, making sure the ground through the resistor, then to here, and then here, that's where power is going to be actually flowing. That's the important part. Like these sense lines where it's just about knowing what voltage is at this point, and even going through a resistor. Like the length of the track is not going to matter there. Let's see, I will have I squared C running along here. I think I'm going to go to the bottom of the board anyway, even though I could do it on the top, because of the I squared C bus that I'm going to have running along there, which I guess on the other hand, maybe I want to do the bottom of that. It doesn't matter. Here, oh yeah, no, there's a layer of ground between us and the diff pairs anyway, so I don't have to worry about that either. Okay, so here, where are we going here? Okay, well, no, it can't fit there. Well, we'll do this, and we'll go along the bottom again. Don't have a whole lot going on down there at the bottom of the board. And we probably don't want to do a whole lot of high frequency stuff on the bottom of the board because we're going to have our lambda grid array, and so there could be potential theoretical crosstalk between the bottom of that board and the bottom of this board if they're right smack on top of each other. But on the other hand, yeah, it'll be fine. Okay. So what is this one going off across here? Is that 5 volts? Yeah, that's 5 volts. So we got to get 5 volts to there. I'll just go along the top layer here. It's important for this ground and this ground to be together, right? It's also probably important for this ground and this ground to be together. So why don't we bang some vias in there and then do the 5 volt around like this, because I think this is just enable this pin here. And so that doesn't need to have perfect power integrity. With these LDOs, it is important to put the capacitors like right next to the LDO, because otherwise you can get like weird cyclical feedback stuff if it's too far away. So yeah, that as far as power integrity with these guys is important. So I think we have a layer for this going there. Yeah. Okay. Well, we're getting close to done. We're getting close to done. Yeah, well, so if we have a dedicated power there, why don't we use it for this too? Okay, what other lines do we have here? I have to turn up the contrast on my screen. It's getting... I still can't see that all that well. Must be a weird thing with the streaming software, kind of changes my... I can't really see the lines. You guys can see the lines looking up at the stream monitor, but I can't see them very well for some reason. Oh well. I guess I can just look at the streaming monitor. Oh, we haven't routed these. Oh, and I put the 5 volt through there. Oh, okay. Well, Odin screwed up there. Now, why don't we fix that? Let's get rid of... Why don't we just get rid of all of it and do it new? Because I haven't routed all those diff pairs there, and putting the 5 volts through there is a really stupid idea. It shouldn't have precedent over them, so we'll just do this on the inside. And then go like there. Because those definitely need to all still be routed. I thought I did all those, but apparently I didn't. Okay, so I guess we're going up to make these kind of the same length, all the way up to like here, and then curling around. So we're somewhat the same length. And we want to move some of the space there. No, I have to go around the other side of that one. Do we want to be super spacey? There we go. Get those to be somewhat the same length. Wow, there's a lot of people in the stream today. Well, we're definitely breaking some records. Even though it's Sunday. Maybe Sunday's a better day. Who knows? Okay, there, I forgot the big one. These don't probably actually have to be this big, but oh well, it'll be fine. If somebody had "it'll be fine" in their drinking game on the stream, they're definitely drunk at this point. So yeah, that needs to be all routed. I really forgot a lot of those. Okay, so we're going around something like this. And then that guy will go all the way down just to make sure he gets longer, and then all the way around and then back. Something like that. And here we're going up top. Oh, it looks bad. Okay. Okay. Oh yeah, there's no way we're going to finish in time because I forgot to do all of these. But no worries. I think everyone can imagine what it's going to look like for me to route the other power over Ethernet controller and the rest of these. So I guess we're more or less just running out the clock at this point. So yeah, tune in next week, next Saturday, for the design start to finish. And yeah, tell people about the stream if you know anyone who might be interested. I'm very impressed by the stream numbers at this point. So thank you all. And make sure and leave comments, ideas, anything and everything you want to learn. I'm not sure if I screwed up the chat or if no one's chatting with me. I don't see any chat. So if you sent a chat, it's not because I don't like you. It's because I don't know how to stream. uh, yeah, anyone and everyone, feel free to just, at me on X or something if you want to get something off your chest, which has to do with this. Okay, so this is a harder portion over here. We definitely want some space between these tracks and the vias that we're going to have to use here. So we'll scooch those down. And then do something like via here. And then go down. I'm not sure which way around it's going to be, so I'm just going to leave that one there for now. And then okay, so I guess we're going around here. And let's move this over here so we can make them about the same length. That's about the same length, right? Oh, crap. Yeah, I guess I'm going to route them on top to get down there. Although, wait a minute, this one's got power integrity relevance as well. So I guess I want to go under this one. Am I going to have enough space to do that? Yeah, that looks like it's working out. I can just do the top the whole way. Wow. That worked out way better than I thought it was going to work out. So how are we going to do this? Could go like that. Yeah, that looks okay. Oops. Another fast with shortcuts thing. If you don't have a track selected and you want to change the layer you're on, like the default or the layer that the new track is going to be at. Like right now, I don't have anything selected, and I'm at the top level, a layer, right? So either I could switch out through, you click on the layer that I want, right? But that's slow, right? So if I'm on the top, I can just hit V and switch the bottom back and forth, right? And then once I'm going away from a via, right, I can hit minus or plus to cycle through the different layers. That definitely makes you a lot faster than actually selecting manually. I think that'll be the last tip of the stream, because it looks like we're coming up on the end. So thank you guys for attending, and I guess I don't have the same delay that I had last time. I wonder why I had the same delay last time. Last time I noticed that I got cut off like 5 minutes before the end of the stream or something. But it looks like, looking at the stream compared to, yeah, no, there's a tiny delay this time. I wonder what I did differently. Anyway, so I guess I can talk for another 5 minutes. Yeah, I hope you guys all had a great weekend, and hope you guys learned something and enjoyed this. And I hope it's not a problem that we didn't actually finish the board. We definitely did all the hard stuff. It's just busy work at this point. And we're not going to look at production file generation and how to specify components and whatnot on this design, but we will in 3 weeks at the end of the next project. Next project is going to be a thermocouple temperature sensor via USB, because I promised the internet I would do it, and it's a good board to do beginning to end. So we will look there at how to specify the components, because anymore I think JLC is probably the best at this point, but there is some American competition coming. It's not just easy and cheap to get your boards fabricated at a PCB fab. If you generate the like the component bill of materials and whatnot correctly, you could also get components mounted pretty cheaply at this point, right? Like, I mean, we used to have a very talented gal soldering our boards, and she was basically half time. She was a student, and she most of what she did was solder boards the whole time. We kept her pretty busy, and so that, I mean, student labor is pretty cheap, but that was like 20 grand a year euro here in Germany with all of the hiring costs. I mean, it's your cost of labor is way more than just salary, right? And so to employ her was like 20 grand all told. And then last year we did about 3 times as many boards, all mounted from JLC. All the prototypes, just don't think about it, ship it and whatnot. And I think our total JLC bill for PCBs and mounting stuff, which includes a couple of products, we do a couple of products with JLC as well, was 17 grand, right? So yeah, it's cheaper than employing someone by a long shot. So I mean, even though she was really good at what she did, she was more expensive. Even though she was as student labor really cheap, and way overqualified as a student. So I have no idea how you could beat JLCM price. So yeah, definitely we're going to have a look at how that works in 3 weeks when we actually order our board. We're going to do all the way start to finish. So yeah, tune in next week. Thanks for. Oh wow, we're at a lot of people. Wow. Then thank you guys. Take care. Have a nice Sunday night or Sunday, depending on what time zone you're in. And I think the stream to YouTube didn't work, so I'm just going to upload it to YouTube. And thanks for all the people streaming on X. Bye, guys. Take care.